So I can start. I am going to talk about basically what I've done the past year. It's going to be a little modified version of what my annual qualifying update is for my committee. So here's a brief outline of what I'm going to talk about. Probably the most interesting part is the first part. I'm going to talk about the physics of what Pioneer is, and Pioneer is the experiment I work on. And I'm going to get more into what I do and what I've done. I work on developing the data acquisition system. I've divided this up into a few kind of soft topics for you. So first off, what is Pioneer? Pioneer is a Pion experiment set to run, I think, 2030-ish is our first main run. And it's focused on the leptonic decays of pions. So, by the way, at any point in the presentation, feel free to interrupt me with questions. So it's focused on the leptonic decays of pions, which is only really two channels, pi to e nu and pi to mu nu. Because the tau decay is forbidden, we're using low energy pions, low momentum. So they don't reach high enough energy threshold to decay into taus. And the muon decay is much, much more likely. Just a little bit counterintuitive, I'm going to explain why that is. It has to do with helicity suppression, which is the idea that the weak force only interacts with left-handed chiral particles, more like a consequence of that. So kind of naively, you would think if you're doing a 3-by decay, you calculate the decay rate for that, you'd see it's proportional to the momentum of the particle. So you'd think the electron decay would be much more likely. It's lower mass, so it has much higher momentum. But that's not the case. So like I said, it has to do with this weak force coupling to left-handed chiral particles and right-handed chiral antiparticles. And that is just an experimental fact, as Dr. Edis has told me before. Neutrinos are all left-handed chiral, which is another experimental fact. So, just a reminder of what helicity is. Helicity is the projection of the angular momentum of a particle onto its momentum. So, if I say something has negative or left-handed helicity, that means the momentum and angular momentum disagree in direction, like this picture. So for zero mass particles or low mass limit, the chiral states are the same as the helicity states, up to some factor. So that means all this neutrino in this decay, this positive pion decay, is guaranteed to have negative helicity. And by conservation of momentum, we know the lepton also has to have negative helicity. That all makes sense? Okay, I skipped a lot of math, but if you go through the field theory calculation, you can show that the left-handed helicity antiparticle, and if the chiral basis is written, that top equation there, you can write it like that. And since you know the weak force only acts on the right-handed term of antiparticles, you can calculate the contribution of this particle to the matrix elements, and you'll see that if you go through the math, which I have in some backup slides, but I'm sparing you, the lower the mass, the more suppressed the decay rate is. So electrons have lower mass, so they'll have a smaller decay rate compared to the muons. So that is what helicity suppression is. Okay, so now I'm going to talk about lepton universality, which is the idea that the W boson's vertex factor for the leptonic decays is the same no matter what the lepton is. So here I've labeled it GE and G mu of what that vertex factor is, and in every textbook they just set them to 1. They're just ignored, but they're all supposed to be the same according to lepton universality, which is an assumption of the standard model. So if you assume they're not for a second, you can use the Feynman rules to calculate the the matrix element for this interaction. I put in this GL for the vertex factor. And again, I'm sparing you the math details, but if you go through the details, you can calculate the matrix elements and use Fermi's golden rule to calculate the decay rate. So the goal of this calculation was to compute this branching ratio I highlight at the bottom. And the reason we're interested in this branching ratio is because this is an experimentally measurable thing. It's the decay rate of pions to electrons and pions to muons. You can simply just count that in an experiment. So this is an experimentally sensitive probe to lepton universality. If we measure this and we see a disagreement with the theory, theoretical value, then that is evidence that lepton universality is violated. So that's why this experiment says sensitive to new physics. Talk a little bit about the theoretical branching ratio. I'm not going to go into how it's calculated, but the idea to calculate the theoretical branching ratio is you use that same calculation I just did, but there's some other corrections. There's a pion effective field theory that you can use, and I don't know much about it, but that gets us to what this theoretical value is, and you can calculate its uncertainty based on what parameters you use there. And that uncertainty is a factor of 10 more precise than the current best experimental uncertainty. Is everyone still on the same page as me? Okay. So Pioneer is expected to improve this value by a factor of 10 and kind of catch up with the theoretical uncertainty. So to describe how Pioneer can actually do that, I'm going to talk about an older experiment, the one that has the current best value for this branching ratio, PINU. And I don't know too much about it, but I'm going to just say they basically shot a pion beam into a sodium iodide enclosure. And because their calorimeter, which is the sodium iodide, wasn't segmented, and they used as a kind of like a long decay time, they had issues of pileup. They also have some systematic errors that they couldn't get around that I'll talk about. But as a result, they had to run the experiment at a low rate, which affected their statistics. Now, Pioneer, to improve that, first our calorimeter, we're going to use liquid xenon or LISO, which is going to be segmented and has a shorter decay time, so we have less issues of pileup. So we can run at a higher rate, so we can get higher statistics. Also, we're going to use an active target, which will help us differentiate between pi to mu e and pi to e. And you can kind of look at this plot. This is the energy distributions for the two decays, and it looks like there's no overlap. But, well, first, let me just show you. This is kind of imagination of what the experiment will look like.
What's LISO?
LISO is a scintillator crystal. I kind of think it's worth going through the extra slide I have on this. It's a scintillator crystal that is basically useful for making calorimeters. I have some sort of slide on it, this thing. So it looks like that. It has these properties. It kind of contains showers and stops particles in a really small kind of space. And it also has a good enough light yield that you get a clean signal, which I'll show that too. Does that answer your question? Okay. All right, back to where I was. So this is the kind of a logarithmic version of this plot I showed, where I said, okay, well, there doesn't look like there's much overlap, but if you look at the log plot, there's a lot of leakage of the pi to E spectrum. This is a monoenergetic electron spectrum, and this muon spectrum. And the leakage is what? It's suppressed by like a factor of 10 to the minus 4-ish, because the electron decay is 10 to the minus 4 times less likely than the muon decay. But since we're trying to make this experiment very precise to improve the precision of the measurement, we actually care about this kind of small overlap, and we really need to understand the what we call the tail of the electron or positron spectrum. So, in an ideal world, the electron or positron deposits all its energy, which should be exactly 69.3 MeV, and that's where this peak is. But due to escaped energy and stuff, you have this tail that goes one way, also radiated decays of a tail that goes the other way. So you can have more energy. The muon-Michel spectrum has this same issue, but that issue can be more mitigated by improving your calorimeter's energy resolution, which is one part of what we focused on during 2023 PSI test beam, which I'll talk about. And this kind of works in conjunction with this active target, which neither of these two, a really effective calorimeter and an active target alone can't give you the precision you need, but when you combine their information together, you can get rid of this systematic error of misidentifying a pion decay to an electron as a pi to mu or vice versa. So, again, just to rephrase, the issue you can come across is if I read a 40 MeV particle, I don't know if that's an electron or a muon up to 10 to the minus 8th precision, but I need that precision. I need that level to make this measurement. So we need to properly identify what they are. So we use this active target, which is in kind of an array of, plates that particles will deposit energy into, and we kind of trace out, is this particle a pion, did it decay into a muon, or did it decay right into a positron, and so on. So we can better classify these events.
So the larger the energy, the more it will travel in that target? Is that what the point is?
The larger the energy? No. It's just that, ideally, if you ignore the in-flight decays, ideally we stop the pion, and then we stop the muon in the target, and it decays into a positron, which deposits energy in the calorimeter. But we want to know, well, did it decay from a pion and then go to a positron, or decay to a muon? Or I guess here it would be a muon and then a positron later out there. And it's hard to tell that just from the energy spectrum alone, because you could have where it deposits 40 MeV and you don't know what particle it is. But this active target gives you the information that you'll see a particle move and then stop, and then decay, and then another particle moves and stops. Because you have these arrays of plates that tell you that information. They kind of track the particle. Does that make sense? Anyway, it's a way to get rid of the systematic error of misidentifying events. And this is kind of a framework, a software framework we use to handle all the different detectors and kind of put them in one software-controlled place and get all their data into one event. So I basically link all the software of all these detectors into one place. I'll talk more about that in a bit. So now into the less physicsy stuff and more of what I do. So the collaboration to build all these different calorimeters and different active targets and whatever other detectors you need, they need to test things. So to test things, they need a data acquisition system. We're building a data acquisition system for the whole Pioneer experiment. But in the meantime, we need kind of like a lower level data acquisition system just to get people running. So part of what I do is develop that. So we're kind of piggybacking off G-2's data acquisition system, if you know about that experiment. That's what my advisor, Dr. Tim Gorringe, worked on before. So we're kind of stealing the hardware we used from that and the software and modifying it so people in the collaboration can use it for their tests. And really, they piggybacked off CERN's. This stuff is like from 1980. It uses telecommunication crates, which CERN piggybacked off the telecommunications. So it's really from like 1960 when you think about it. Anyway, I kind of divided up into a hardware and software side of what I work on. So just a picture of the hardware side. I'm not going to explain any of this really, but just this is the kind of stuff that goes into a crate. You have all these digitizers you put your signals into, and it spits out data. And then I read it out on the software side. It's just a list of some adjustments I had to make. This is a picture of some stuff you can do. This is a data quality monitor web page. It'll just take the signal you see and print it on a screen for you, live updating it. Some things I had to add for convenience for people in the collaboration. I just generalized some code too when I was doing that along the way from the G-2 code. And also you have to write a ton of documentation just so people can actually use your software and set things up. So I've also written basically a Wikipedia page on this at this point, but I still get 1,000 questions, so I don't think there's any way around that. And here's a picture, I guess, of one of the use cases. This is at the University of Washington at the Center for Nuclear Physics and Astronomy. I don't think they do any astronomy though. And it's rainy, so we all look a little messed up. But anyway, there's currently 4 places we're using it at the University of Washington during the 2023 PSI test beam, which I'll talk about. There is a liquid Z9 tests at Triumph, which is Canada's National Particle Accelerator, and some other experiments at Paul Scherr Institute, which is PSI, which I won't talk about those experiments, but I'll talk about PSI right now. So for a month in November of last year, they shipped me to Switzerland to PSI, so we could do measurements on these LISO crystals that Ryan asked about to determine their properties and, I guess, adequacy as a candidate for a calorimeter and Pioneers experiment. Particularly, we're interested in the energy resolution. And it's really kind of a simple experiment we ended up doing. You just have a beam that you tune of some quadrupole magnets. There's a ton other quadrupole magnets down the line. You're basically just bending some beam into your experimental area and adjusting the magnets to get what momentum and shape you want. Once you have that, you send it through, a veto and a T0. So the veto is just saying, okay, if there's a particle, I don't see it in the veto that's outside of what I want. Like I don't want a particle coming in from like this way. So it has to go through the veto. There's a T0, which is just a timing starter for everything. A hodoscope, which I'll describe, kind of gives you a beam profile, and then it goes into our calorimeter, which is this array of LISO crystals with some leakage detectors just around it. And all that goes into the data acquisition system, which I had to kind of design to take all this data and turn into something sensible. This is actually what the picture looks like, of what it really looked like. This is the hodoscope 4, and 6, and what was that, 5 are the calorimeter. The beam's coming out of that big red thing.
So does that data acquisition system have its own compression algorithms that you go through?
Not this one, because we didn't need it. There's not enough data. We only got, this test was only 2 weeks of beam time. I think we got 2 terabytes of data out of it, so we didn't bother compressing it. Just bought a couple drives. Anyway, so this is the LISO calorimeter part. I already talked a little bit about these parameters. So this is what looked like we had this array of 10 crystals shaped like this, so we could shoot the beam kind of somewhere in either the middle of 4 or 5 and have it surrounded well enough within a radiation length or a Moliere radius. And it makes a pretty clean signal for 50 MeV, which is kind of our little close to our nominal, 69.3 MeV that we expect from the experiment. Yeah.
What do you use to read out the energy that you get in your calorimeter?
There's some photomultiplying tubes behind it. I don't know exactly what type of photomultiplying tubes they were, but
Why tubes and not something like silicon photomultiplying?
Well, we do use those for the hodoscope, which I'll talk about, I guess, but I don't know the details of why they chose the PMTs they did for the LISO crystals. This was kind of University of Washington's contribution. But there were problems with it. They were non-linear, which caused problems. That's neither here nor there. I guess the short answer is I don't know why. Specifically, we use those. So this is the hodoscope, which is the thing which I described, creates a beam profile image. The way it works, you kind of have 12 channels this way, 12 channels this way. So if I get a hit in one channel here and a hit in a channel here, then I know the particle kind of went through their intersection. So I can trace out a beam profile that way. And these do use silicon photomultiplying tubes connected to some plastic scintillators, and they don't have good energy resolution, but they'll tell you if something went through it. And you can combine this kind of beam data and move your array of LISO around to trace out how the energy deposit looks depending on where the calorimeter is relative to the beam, which is very useful. The last thing I'm going to talk about PSI is the energy resolution. So this is the big measurement we ended up getting. We got an energy resolution of 1.55%. So this is kind of like the width of this curve over its kind of peak value. The fit's kind of funky, but it's more or less like a fit of a Gaussian at the top to get your width. And this value is over 2 times better than the previous best value reported, which actually has a lot of implications in medical physics. You can use this to detect cancer and stuff. When they make you drink that radioactive stuff, you can kind of put them in a room of LISO. But anyway, I digress. So this is really similar to liquid xenon, which means we knew we could use liquid xenon because other experiments have done similar things. But now we know we can use LISO as well. So there's kind of, within the collaboration, a choice of to use LISO or liquid xenon now, which I don't deal with. I still just make the data acquisition system either way, which I'll now talk about.
Can I ask
Yeah.
that last slide? Is that the non-linearity you were talking about at like 20 MeV on the bottom right corner?
No, this is a different beam.
Or is it? Okay.
So they corrected for the nonlinearity. If you want, you can read this paper up at the top. Memorize that archive number real quick. But they talk about the nonlinearity of how, as you increase the energy, the response from the photomultiplying tube is not linear, it kind of curves up.
Okay, so that's just a different beam.
Yeah.
Okay.
I don't quite know why that in particular is different.
Okay.
Anyway, so when I like to think of the DAC, I like to think of a hardware side and a software side, which I kind of showed you the crates and the software. Where we're in a collaboration, so Cornell's job is mostly to handle the hardware side, because they have like 20 engineers, and our job is to just handle the software side, because we have like 0 engineers. Got one me. And so the goal is to kind of like build these systems and kind of bridge them together, which means we both need knowledge of what each other are doing. So part of what I have to do, which I'll talk about, is I have to build simulators for the hardware. So this is kind of the proposed framework. If you look at the proposal, this is the conceptual diagram. I'm not going to talk too much about what all this means, but just know this top stuff is the hardware side, and the bottom DAC system is the software side, which has to have two-way communication of all these components. So I need to be able to send control information, get the data out, and it can send other information besides data to me, and needs to be able to sort itself out, initialize, and all of that. Now, the part I work on is more of this. This is all software. So there's a readout library, which we're going over PCIe, which is the it's a really high data throughput thing on your computer. If you ever built a computer, it's what you plug in the graphics card into. So once you get the data into reading it out through PCIe, you send it into Midas, which I briefly talked about, which its job is to just assemble it into an event from all these different sources, bundle into one event, which then gets written to a file and put into storage, or that file gets into the near line analysis layer, which is like a first level analysis to look at things like traces and build histograms just to see is your data actually what you expect it to look like, but not any rigorous analysis that you put in a paper, just to check that everything's working. So this is the hardware, which again, I'm not going to talk too much about this, but it's just for reference. That we're moving away from that micro TCA 60-year-old system I described into a more modernized system called Apollo system. This is also piggybacking off CERN. I don't know where they got this from. I think they designed this one themselves. But the idea is you move data over this Firefly system, which is an optical cables overlaid over your boards. So this allows for you to transfer data really quickly, 25 gigabits a second, but also it's very noise resistant because it's an optical signal. You don't have all these high voltage signals flying around your serial lines causing noise that you don't want to deal with. So that just makes everything much faster overall. So to simulate some system where we're reading data out over PCIe, we need kind of a data generator on one end of the PCIe and a computer to receive it on the other end. So what we use for our mock experimental hardware is this development FPGA. FPGA stands for Field Programmable Gate Array. For those who don't know, it's like a little computer you just put on a board. But you can program it. So we have this FPGA that talks to the computer over PCIe, and there's some RAM and that you can store data in temporarily, and FMC is like FPGA mezzanine card. It's just like an expansion slot that you can put like analog digital converters onto to send in real signals if you want. But this board we're using just because it's simple to use, and although it's very slow and not really similar to the real experiment data rates, it provides a system for testing at least. I'm not going to talk too much about this either, but this is the we need to program this, so we use Vivado, which is the way you program FPGAs. These are these intellectual property blocks that if you magically arrange into this configuration of runes, you will create a device that can talk over PCIe. Anyway, so then you can measure how fast can I transfer things with this particular FPGA. So I can read out over one channel at about 700 megabytes a second, and you can go over two channels, but that doesn't double the rate because of some talking issues, or I don't know how to describe it. The point is I get about 1 gigabyte a second out of this card in specific, which is the experiments expects a data rate of around 3.5 gigabytes a second. So we're in the right ballpark just with this kind of terrible, low, cheap design that we've decided to do for testing. I'm going to talk a little bit about compression now, so I'm kind of shifting gears. But when we generate data at 3.5 gigabytes a second and you run your experiments for a third of the year, that's what, 40 terabytes, 40,000 terabytes or something a year? Something like that. You can't store all that. So what we need to do is we need to take the signals and compress them. So the easiest kind of way to visualize doing that is you have a signal and you just fit it. Then what you're left with is the fit parameters and the residuals, right? So before I had a space that could be taking up negative 1800s, like 12 bits or something, although the signal's much smaller. It would take 12 bits to encode that signal above. But if I just store the 3 parameters and all the residuals, I've reduced that range to about 16 values, so about 4 bits. So just by doing that, naively I've compressed things by a factor of 3. So now we're down to what, like 10,000 terabytes a year, which is still not very doable. But
You said something about 3 parameters? What was that?
oh yeah, so with a template fit, you basically have a bunch of signals that you construct a template out of. So you just take all your signals, you kind of align them, average them, and then you fit some sort of function like a cubic spline if you want, some interpolation. and then you can shift and stretch that to match your whatever signal comes through. So your template fit is just shifting and stretching a template to kind of match whatever real-time signal you have. So it's fast is one advantage of it because it's just a linear fit. And it's really easy to parallelize with GPUs, which we will do in our final design of the Pioneer data acquisition system. Does that answer your question? Yeah, so there is a shifting of the time of the template. So I guess you can imagine your template is this shape, and you shift it on this x-axis, and you can put it on a pedestal, and you can also stretch it upwards. You shouldn't need to stretch it sideways because these scintillator crystals have a very consistent kind of decay time. Okay. So this is that template fit applied to a PSI data set, not the whole thing, just one run. So I think it's about 1 million samples, give or take. So this is what a heat map of it looks like before you've template fitted it, and then after you template fit it, you can see you've made this range much, much, much smaller, which makes it much easier to compress. So computer scientists, for lossless compression, have already figured out what the best compression you can do is. It's this thing called this entropy rate formula. It's just this formula that if you go through each kind of time, you can calculate the entropy of that time in the signal. So if you're just at the pedestal, which is what I call the part without the signal, kind of these parts out here, just the noise of your system causes about 3.4 bits of entropy, which means the best you can do is 3.4 bits, even if you had a perfect fit. In this system, the noise might be lower in another system that we use in the future. So now we've gotten our 3.5 gigabytes a second down to about 1 gigabyte a second. So now we're down to what, like 8,000 terabytes a year? So possible, but still a pain. Anyway, are there any questions on that at all? Yeah.
When you calculate entropy, you have to use a probability distribution of xi.
Yeah, you can construct that from your data. So each kind of vertical slice is your PXI. So at time 0, you time align all your signals. And I'll say at time 0, you construct what a PDF of what your signal is at that time. And then you can compute the entropy at that time and then make a plot like that.
Okay.
So it's just a bunch of vertical PDFs kind of.
So these are empirical distributions.
Yes, these are empirical in a sense, but what do you mean by that exactly?
Well, I don't know if you're feeding it like a cumulative distribution function or actual.
No, it's constructed from data, is what I mean when I say empirical, but okay. It's a good approximation of what a compression will be for the actual experiment. Okay, so this is my last couple slides, just what I'm working on now, what I plan to work on. So another data acquisition system for the active target, they can't really use this piggyback off of G-2, so they need this thing called this NALU HD SOC digitizer. Some company in Hawaii makes it. But I have to take that and integrate it into this MIDAS system we have to be kind of another data source that gets put into events. It's pretty straightforward so far. They have their own Python library. So it makes things much easier than dealing with this terribly written G-2 code, which I've had to deal with. I showed you that block diagram before. This is another magic moon rune diagram that will add what's called a microblaze to your FPGA, and that allows me to write C++ code on the FPGA to do things like write data simulators and do whatever I want to the memory on board. So it can be read out from the FPGA to the
Before you use the microblaze block, were you writing in machine code, or how are you programming the FPGA?
Yeah, that's a good question. The FPGA is coded in programs using something called Verilog in Vivado. I don't really write much Verilog because each one of these blocks corresponds to like a block of Verilog code, and you kind of link them together, and that creates the firmware. The microblaze is a block of Verilog code that allows you to write C++ code to the FPGA. The benefit of that is that C++ is a higher level language, which allows me to more easily kind of access like memory stuff, and it gives me more freedom. I don't have to literally is a bad word, but wire things up with a custom block. I can just write some whatever C++ script I want to be a simulator, or whatever I need it to do. Okay, so more things I work on is all the software I write. I try to make it as modular as I can because, again, reading through G-2's code base is terrible. It's all kind of interweaved, and you have to really kind of break things to make things new. Where the idea is if I write all these libraries that kind of each front end corresponds to some detector, like one is your active target, one's your calorimeter, and so on and so forth, you can kind of just give them whatever library they need to do their job, and that way it's not all interwoven. It's more plug and play, plug, unplug kind of deal. And all just goes into Midas to generate these events. And this is probably the last thing I'll do for my PhD. The Pioneer demonstrator is a full demonstrator because, like I said, the experiment goes on 2030. I don't want to be here still then. So the Pioneer demonstrator is in 2026. And it's kind of like a prototype of every detector in one experiment. It doesn't actually do the experiment, but it shows, hey, everything works. The idea is to get some data out of that to analyze. All right, that's pretty much all I have.